So let's now take a look at some basic exponential expressions and look at what do the values in exponential expressions actually represent. So let's start with the function of x is equal to, say, 200 times 2 to the power of x. So our variable here is an exponent, making this an exponential function. Well, when we're looking at this, what does the value of 200 actually represent? And what does the value of 2 actually represent in our function? And that's what we're going to explore today. To begin with, I want to consider this value of 200. What does that represent? Well, to explain that, let's look at when we input the value of 0 into our function. So this would be 200 times 2 to the power of 0. Now, we know 2 to the power of 0 is equal to 1, so it's 200 multiplied by 1, and anything times 1 is just what it was, so our f of 0 is equal to 200, which is that value at the front. So when we input the value of 0 into this, we end up with the output of 200. Well, let's consider that. Let's consider that when we're dealing with, say, populations. And I often consider, when we're looking at exponential functions, to remember it, I think about populations. Let's say we've got a population with respect to time that's equal to, say, 1,000. And our population here is going to be multiplied by 0.5 to the power of t. Well, let's input our time period of 0. Our time period of 0 would be our initial population, so when time was 0. So the p of 0, well, that'll be equal to 1,000 multiplied by 0.5 to the power of 0. Now, anything to the power of 0 is equal to 1. So this will be 1,000 times 1, which, of course, is equal to 1,000. So as you can see here is, when I input my time of 0 and end up back to this first value again. And that's what our first value always represents. It represents the state of the expression when my input is equal to 0, which is the same as saying my initial value. So if I was to write this more generally, let's say I've got y is equal to a times b to the power of x. My a value here, this a value here, is the starting value. Now, the starting value, when I can spell, is the same as saying it's the initial value. So you might hear that a bit. It's the initial value or the starting value. But it's the value that occurs when my input of x is equal to 0. So what about our b? Well, our b is known as the common ratio. But to understand what the common ratio actually means and what it represents, I like to think about populations. When our b is greater than 1, we've got a population that's going to be growing or increasing. But when it's less than 1, we're going to have a population that's decreasing or decaying, as we call it. Now, I'm only going to consider when b is greater than 0. I'm not going to worry about when b is negative. But to help explain what the common ratio is, let's first consider what would happen if my b value was equal to 1. Well, let's think about 1 as a percentage for an example. 1 as a percentage is 100%. What that would mean is if my b value was equal to 1, my population here is going to be stable. It's not going to be increasing, it's not going to be decreasing, it's going to be staying the same. And if you think about that mathematically, if b was equal to 1, it doesn't matter what power I raise b to, this part of my function will always equal 1. 1 to the power of negative 3 is equal to 1. 1 to the power of 0 is equal to 1. 1 to the power of 20 is equal to 1. So you always will have y equals a multiplied by 1. So y will always be equal to a. It'll always be the same. It's not increasing, it's not decreasing. However, when you increase this value, so increase it to 2 for example, well 2 as a percentage is equal to 200%. It means that for every increase of my exponent of 1, I'm going to increase my initial population by 200%. Now, that doesn't mean I've got 200% growth that's occurring, it's just it's increasing by 200%. If I was to look at how much growth that is, well, I take my initial percentage of 100% and I'll look at, well, how much percent would I need to add on to get to this 200%? And that would be another 100%. So in terms of growth, this represents how much growth I've got. All right, in this case, I've got 100% growth to get to that value of 2. However, in this example here, it was less than 1. It's still greater than 0. I'm not worried about it when it's negative, but it's less than 1. It's 0.5. Well, 0.5 as a percentage is 50%. It means that for every one time period it increases, my population is going to decrease every single time. It's only going to be 50% of what it was before. It's halving every single time. Now, to look at how much it's decreasing by, we've actually got to do the opposite. We've got to have our 100% that we started with, our 100%, and we've got to look at subtracting this value to work out how much it's decreasing by every time. So in this case, we're subtracting 50% to get to this, which means that we've got 50% decay in this one here. But to understand this decay part just a little bit better, let's just take another population. Let's say we've got the population with respect to time that's equal to 500 multiplied by 0.8 to the power of t. Now 0.8 is 80%, so it means that our population, we're multiplying it by 80% every single time. But we can start interpreting some values out of this now. We can say that our initial value, our initial population, is equal to 500 here. It's that value of A. And like I said, that 0.8 represents 80%. There's 80% remaining every single time period. But if I want to look at how much growth or decay is actually occurring, obviously it's decay because it's less than 100% remaining every single time. But to work out how much is decaying by, what I've got to do is I've got to take 100% and subtract however much is here. So it's this 80% that was remaining. And that will tell me how much decay there actually is occurring every single time. So to summarize, the basic exponential function of y equals a multiplied by b to the power of x, our a represents the starting value, also known as the initial value, and our b is known as the common ratio. But I like to think of b as how much it's growing by if it's greater than 1, or how much it's decaying by if it's less than 1 but greater than 0.